is the first video in AP Calculus for section 4.4 in our textbook, which is on modeling and specifically optimization. So when you think of the word optimization, I hear optimize or make the most of something, and that's essentially what we're doing with optimization. We have typically real-world situations where we're trying to either maximize or minimize whatever the situation is going on. For example, if it's a profit function, we obviously would hope to maximize it. But if it's a cost function, we might want to minimize it. So what you see on the screen here are the 6 general steps that you can go through in solving these optimization max-min problems. It's very similar to finding the maxes and minimums that we've been doing just in general functions for their graphs. The only difference is that since it takes on usually a real-world aspect, it's not all just handed to you. And I wish that I could say that I could make a video going over every single possible type of word problem that you could have in optimization, but that's just not possible. You're going to have to learn to problem solve for yourself and create the equations and create the relationships and really make those connections yourself. I can't show you one of every single solitary type. It is 100% impossible to do. So understanding the problem-solving process is going to be key. So you want to first make sure you understand the problem. Read through it carefully, probably multiple times. Extract the information that you're going to need in order to solve the problem. Then develop a mathematical model. That oftentimes will include drawing pictures, labeling the important parts of the pictures, creating variables to represent your unknowns, and then eventually writing a function whose extreme values are what you're looking for. In fact, and I put this in the box off to the side, often 2 equations are going to be needed. A lot of times you'll have the one equation based on what you know, some sort of other relationship, like a side relationship, and then another equation based on what it is that you're trying to maximize or minimize. Step 3 can be to graph the function, determine the domain. That can and cannot be used. A lot of times it's just a common sense relationship. You don't necessarily need to look at the graph for that. The number 4 is to identify the critical points and the endpoints. So that's where we're going to find the derivative and find where it equals 0 or does not exist, all that stuff we've been doing. Then we'll solve the model, and then we'll interpret our answer in the actual context. So if our answer is x equals 6, well, what does that 6 represent in this particular problem? That sort of stuff. So that's your problem-solving process. So we're just going to look at some examples here in these videos. Like I said, I can't do everything, but I'm going to try to do a variety of problems. So we're going to start simple. Example 1 wants us to find 2 positive numbers whose sum is 24 and whose product is a maximum. So I need 2 numbers. We could call them x and y. A and b, you can pick whatever letters you want. So I'm solving for those 2 things. I want to know what they're equal to. Whose sum is 24. So x plus y is 24. Sum means add. And whose product is a maximum. So I'm going to multiply them together to get some sort of product. That's the function that I'm trying to maximize. So thinking about maximums with graphs, maximums occur where the derivative is equal to 0. So, or where it does not exist. So I am essentially going to want to take the derivative of that p equals xy equation. The only problem is that it currently has 2 variables in it. When I'm taking the derivative without having to do implicit differentiation and all that, I can only have 1 variable in there. So that p equation needs to be written either all in terms of x or all in terms of y. So that's where this little side equation is helpful to us. I have another way that x and y are related by x plus y equals 24. So for example, I could solve it to say y equals 24 minus x, and then I could replace this y with 24 minus x. So that means that p would be equal to x times 24 minus x, or p equals 24x minus x squared. Now as far as taking the derivative of p, it's really easy because it's all in terms of x, and I can just use the power rule. So 24 minus 2x is a linear function. There is no place where it doesn't exist, but I can look for where does it equal 0. So x is 12. However, I'm not done with the problem. The problem was to find two positive numbers. I found one of them. So then I go back to here. And if I substitute the 12 in for x, then I get that y is also 12. So it's always a really good idea at the end of an optimization problem to write your final answer as a sentence. So you could say the two numbers are 12 and 12. And the problem did not say two different numbers, so it's okay that they are both 12. Okay? All right, now we're going to look at another, this is an algebra-based problem. It says a rectangle is to be inscribed under one arch of the sine curve. What is the largest area of the rectangle, can have, and what dimensions give that area? Okay, so they want, basically I'm looking, that pink thing right there is a rectangle, and I'm trying to maximize the area of it. So area of a rectangle is length times width. Here is the length, here is the width. And just like the last problem, the problem with this function I'm trying to maximize is that it's got two variables in it, an L and a W. So I need to find another way to relate those things to each other, either to each other or to some other common variable. So here's where it's important that this black arch here is the sine curve. So that means that this point right here, for example, is sine of whatever this x coordinate is. And this point right here, its height is the same as this height. So it is also sine of x. Well, that measurement right here and right here, those are my width. So my width is sine of x because it's as tall as my function is at whatever that x coordinate is. I don't know where that x coordinate is right now, though. Unfortunately, I've now introduced a third variable into the relationship, sine of x. So I've got this x in here now. So now it would be great if I could figure out a way to represent L also in terms of x. So I'm going to look along the x-axis. Let me erase the stuff that I've already drawn here so that you can see where I'm going with this. So this right here is L. If this is x, then that means that this right here is x units long. That also means that since the rectangle fits symmetrically under the arch, as we can tell by the graph, that is also x units long. Okay? So this entire length all the way across is x plus L plus x. So if I know how long that length is, then I can figure this out. Well, that entire length is one arch of the sine curve. So this is where you have to know your graph of sine. Graph of sine starts at 0 at 0, 0, and then it goes up and it comes down. The next time that it touches the x-axis is at pi. So my total length is L plus x is equal to pi, or L equals pi minus 2x. So bringing this down, that makes my area formula pi minus 2x times sine of x. And as weird as that looks, the good thing about it is that now it's 100% in terms of x. So to take the derivative of it now, I can simply do product rule. So I would do the first function times the derivative of the second plus the second function times the derivative of the first. And since pi is a constant, the derivative is just going to be negative 2. So that is a prime, pi minus 2x times cosine of x plus negative 2 sine x. Okay? Now, this is where you're grateful that the majority of these optimization problems are going to be calculator problems. The last one we did 100% without a calculator. But at this point, solving this one and setting it equal to 0, you're going to need a calculator for this. So you're going to graph in your y equals pi minus 2x times cosine of x plus sine of x times -2, and you're going to look at where it crosses the x-axis. Now, it's going to cross the x-axis at lots of spots, but what we know is that our x value has to be between 0 and pi, based off of the fact that we're in that first arch of the sine curve. So if you graph it, you will get x equals 0.710 as one place between 0 and pi that it crosses the x-axis, and 2.431 as another place that it crosses the x-axis. Now, only one of those am I going to keep, though. This right here would be 0.710, which would logically make this 2.431, but only because the first point was 0.710. So we're actually only going to keep the initial x value that we got of 0.710. Now that we've solved for x, we need to go back and read the problem again to figure out what exactly it is that they were wanting me to answer. So it says, what is the largest area the rectangle can have, and what dimensions give that area? So they're looking for what the area would be, and for dimensions, they don't care what the x is. They want to know what the width would be and what the length would be. So the area would be pi minus 2 times 0.710 times the sine of 0.710. We would substitute our x into our area formula, and we would get 1.122. And then the width is sine of x, so sine of 0.710, and we would get 0.652. And then the length is pi minus 2 times 0.710, and we would get 1.722. And then when you have multiple things that are being grouped as answers, it's not a bad idea to maybe put a box or something around them so that it's easy for you to find later on, or easy for the person grading your paper to find those answers. All right, so I'm going to end the first video right there, and I will make another video with some more geometric applications of optimization.